Welcome back, everyone. This is the second of 3 videos where I go through all of the content in the handout that I gave you in class called Math 30-1, The Straight Poop. In this video, we're going to be covering Unit 3, which deals with trigonometric functions, and Unit 4, which deals with trigonometric equations and identities. Just like the first video, the purpose of this is not for us to practice a whole bunch of math. In fact, the amount of math problems that we do as I work through this handout will be very limited, if any at all. The purpose is to go through all of the content, all of the concepts that we covered in Math 30-1, so that at the end of the video, you're better prepared to answer all of those review questions I've given you in class. Many numerical response questions, many multiple choice questions can be turned into written response questions. We've spoken in class extensively about what's expected to get a good mark on a written response question, and I'm not going to go through that with you now. So let's get started here. In trigonometry, you need to know what some common angles are. Now, you need to know that 180 degrees is pi radians, not because someone is going to ask you that on a diploma exam. But if you don't understand that basic fundamental idea, or truth, then you're not going to be able to apply that and solve more complicated problems. So this is our starting point. Angles can be measured in degrees or radians. 180 degrees is the same thing as pi radians. Half of pi would be half of 180, so that means that 90 degrees is pi over 2. 60 degrees is only a third of 180, so pi over 3 is 60. 30 degrees fits into 180 3 times. Pardon me, 30 degrees fits into 180 6 times. What that means is that pi over 6 will give you 30 degrees. And if we divide 180 by 4, we get 45 degrees. And that means that pi over 4 is 45 degrees. You need to be able to convert from radians to degrees or from degrees to radians, and there are a number of ways to do so. And you need to be able to do it with exact values or decimal approximations. First of all, if you have a measure in radians in which pi is part of it, just replace the pi with 180. Quick illustration of what I'm talking about here. If I said, what is 17 pi over 13 in degrees? Well, pi is 180 degrees, so all you would do is take 17 times 180 and divide by 13. In all other cases, I think it's a good idea to set up a ratio where you can write pi radians over 180 degrees equals a new ratio of maybe x radians over 48 degrees, or whatever it is you're trying to convert to. It may not be that on the diploma exam you're going to be asked, what is the degree measure of a particular angle? Or what is the radian measure of a particular angle? But you're going to need to know how to convert from radians to degrees or degrees to radians for other reasons. One of them is because of arc length and how we work with arc length in this course. Arc length is defined as the distance around the edge of a circle over a particular sector. And the sector is defined by rotating a radius of the circle through a particular angle. So when we rotate that radius through an angle, that arc length, that curved length that I've indicated, is obviously connected to the angle and to the radius. I think if that theta were smaller or bigger, you would recognize that the arc length would be smaller or bigger. And if the radius were larger or smaller, you'd recognize that the arc length would be larger or smaller. And there's a mathematical relationship between them. And this is on your formula sheet. The angle subtended by that arc, that's how we say it, that angle in that diagram is equal to the ratio of the arc length over the radius. But, and this is so crucial, you don't want to get burned on something like this on an exam, that angle must be in radians. The formula will not work unless it's in radians. So if you're given a problem on the exam where the angle is in degrees and you're asked to find an arc length, well then you're going to have to know how to convert that angle in degrees into radians. So you're going to maybe set up a ratio. Or maybe you're given a question on a diploma exam where you're asked to find the angle, but you're asked to find it in degrees. And when you use this formula and calculate theta, you'll get an answer in radians, but maybe the numerical response question says, we want to know it in degrees, so you have to convert your radians to degrees. This is one of the reasons why you need to be able to convert radians to degrees or degrees to radians. Rotation angles in standard position. I'm going to talk for a little bit here about things that you learned actually in Math 20-1, which form a foundation for some things we do in 30-1. A positive rotation angle theta in standard position has the following properties. The initial arm is on the positive x-axis, and if it's a positive angle, it's rotated counterclockwise, indicated by that diagram that you're looking at. If the angle is a negative rotation angle, it's rotated clockwise. This is a review from 20-1. A negative rotation, as I said, is a clockwise rotation. Reference angles, also an idea from Math 20-1. However, it's an important idea that we continue to apply in 30-1. What a reference angle is the smallest positive angle between a terminal arm and the x-axis. And I want to make something clear here. It has no direction. A reference angle is just an angle. If you have a terminal arm in quadrant 1, then the reference angle is what's indicated there by that black arc. Do not worry about the red arc just yet. If you have a terminal arm that's in quadrant 2, then the reference angle is indicated by that black arc. It's the smallest angle between the terminal arm and the x-axis, which in this case would be an angle down towards the x-axis. If you have an arm that terminates in quadrant 3, there's the reference angle indicated by the black arc, and in quadrant 4 there's the reference angle. What those red arcs are rotation angles. And there's a distinct difference between a rotation angle and a reference angle, and one of the things, depending on how you do certain problems, that you may need to know is what's the relationship between the reference and rotation angles in each of these cases. When you look at quadrant 1, whatever the reference angle is, that is the rotation angle. When you look at quadrant 2, in the bottom right corner, the rotation angle could be found by taking 180 degrees minus the reference angle, or the rotation angle could be found by taking pi radians minus the reference angle, if you want to think in radians. In quadrant 3, the rotation angle can be found by taking pi radians and adding the reference angle. And in quadrant 4, if you take 2 pi radians and subtract the reference angle, you get the rotation angle. There are going to be cases on the diploma exam where you will need to know how to find a rotation angle from a reference angle. More often than not, but occasionally you might be expected to find a reference angle from a rotation angle. The unit circle. So what is the unit circle? The unit circle is a circle that is centered at the origin and it has a radius of 1, so this is what it looks like. We talk about rotation angles about the origin, which is that red curve, that red arc, and that green line is simply a terminal arm, but that doesn't form part of the unit circle. The unit circle is the circle that you're looking at that's centered at the origin with a radius of 1. The equation of that circle is x squared plus y squared equals 1. Because of the Pythagorean theorem, it's x squared plus y squared equals 1 squared, but 1 squared is 1. That angle, I've now included in on your view, that angle theta in the diagram is called the rotation angle, and there is a trigonometric connection between that angle and the x and y coordinates of the point where the arm touches the unit circle. The x-coordinate of the point is the cosine of the angle, and the y-coordinate is the sine of the angle. Now, let's just walk away from that for a bit. What do we use the unit circle for? Well, you use it primarily, or most of the time, to determine the coordinates of the points of intersection of a terminal arm and the unit circle for common angles, for angles that are multiples of 30 or multiples of 45 or multiples of 60. And if you know those coordinates, you can determine the exact values of any trigonometric ratio at that point with that rotation angle. Knowing those coordinates also allows you to solve trigonometric equations quickly. Now, I'm just going to quickly go through this with you because I think there is some value in just reviewing how we know what some of these numbers are. You need to, I would expect, know that any terminal point on the unit circle that's at a 45-degree angle has the coordinates √2 over √2, comma, √2 over √2. I want to be cautious here because this could also be written as 1 over √2, 1 over √2, and students often ask, well, which one is preferable? And the answer is neither one. On the one hand, I would prefer √2 over 2 because it's rationalized, but on the other hand, 1 over √2 seems simpler. It depends on the situation, but they're both valid. Then I think my suggestion is that you remember the terminal points that lie at angles of 30 or 60 degrees away from axes will always have the numbers 1/2 and √3 over 2. So if you know that, and perhaps you don't know what these coordinates are, we're not looking at them, they're invisible to us, and you start to focus on this point, you know that this has a y coordinate of 1 because it's the unit circle. So if you extend a horizontal line over to read the y coordinate of that point, I think it's pretty clear that that y coordinate is not 1/2. And just by doing that quick exploration, that quick peek with your eyeball, that tells you that the y coordinate here must be √3 over 2. And just to check this out, if I were to extend this point down to the x-axis, I think you can see that that's intersecting the x-axis at about half of the radius of the circle, which is 1/2. There are certain tips and tricks that I think you can use in order to determine these numbers. Anyway, there's quadrant 1. Here's quadrant 2. The only thing that's different, quadrant 2 is mirrored horizontally by quadrant 1, but of course all of the x coordinates are negative in quadrant 2. And in quadrant 3, x and y are both negative. And in quadrant 4, y is negative, but x is positive. You will also notice that we know the coordinates of the points at 0 degrees, at 90 degrees, at 180 degrees, -1, comma 0. So you need to be familiar with all of these at 270. Now I want to stop here for a second because when we learn the unit circle, we're doing this, what you're looking at here in quadrant 4, because then we can say that if I want to determine, for example, it doesn't really matter, I'll take the sine of 7 pi over 4. Then I know that the sine on the unit circle is the y coordinate, so I look at 7 pi over 4, it's down here, and I look at the y coordinate, so it gives me quick, easy access to trigonometric values. I know the sine of 7 pi over 4 is -√2 over 2. And that's what we get caught up in, and it's a good thing. You need to know that. However, sometimes you lose sight of the simpler things in the unit circle, which is these two statements. And I'm taking a minute here and going back in this handout because we had a question in class the other day where somebody asked, we had a question where you were told that a point on the unit circle is at -0.23, comma k, and it was in quadrant 3. What is the value of k? And again, you get so caught up with that big picture of the unit circle with all the coordinates that you forget that x squared plus y squared equals 1. So -0.23 squared plus y squared equals 1. I'm not going to solve that, but when you solve it, you're going to end up taking for y squared plus or minus the square root of a number. And since it's in quadrant 3, you'll go with the negative of the square root of that number. Similarly, you sometimes get questions that simply tell you a terminal arm has a rotation angle of 328 degrees, what is the x-coordinate of the point of intersection of that arm with the unit circle? Well, the x-coordinate is the cosine of theta. So if I wanted to know the x-coordinate of that point of intersection of that rotation angle, its terminal arm in the unit circle, I'd just take my calculator and I'd put it in degree mode and find the cosine of 328 degrees. So don't lose sight of those things about the unit circle. Yes, it's about the bigger picture, like finding sines and cosines of these special angles, but it's also about these 2 points that are highlighted in yellow. All right, on the coordinate grid, the primary and reciprocal trig ratios are defined in terms of x, y, and r. This is true whether we're talking about points of intersection with the unit circle or not. So for any rotation angle, this one happens to be in quadrant 2, but it doesn't have to be. For any rotation angle, you can pick a point on the terminal arm, and that point has coordinates of x, comma, y. By the way, r is the distance from that point to the origin. Well, we know that x squared plus y squared equals r squared. But from Math 20, you were taught that we walk away from the concept of opposite and adjacent and hypotenuse when we enter the realm of the coordinate grid, and instead we talk about y and x and r. So sine of theta is y over r, cos is x over r, tan is y over x. You know, back in Math 20, we give you those on a formula sheet, but not in Math 30. Well, you need to associate cosine with x and sine with y, and then know that tangent is sine over cosine, or y over x. What was new this year, as well as not giving you these formulas on a formula sheet, is knowing the definitions for the 3 so-called reciprocal trigonometric ratios. And I'm just going to jump ahead a bit here. Cosecant is the reciprocal of sine, secant is the reciprocal of cosine, cotangent is the reciprocal of tangent. So knowing that, if cosecant of theta is the reciprocal of sine, and sine is y over r, cosecant is r over y. All we do is we flip that over. You need to know that secant is r over x, and cotangent is x over y. If the point on the terminal arm intersects the unit circle, then those 6 trig ratios that we're looking at here become simpler. So I want to break this down. What we're looking at right now is for any terminal arm, whether the terminal arm is a length of 10 or 0.3. These 6 definitions in terms of x, y, and r are all valid. If r happens to be 1 because it's intersecting the unit circle, then all of these r's on the screen become 1. So sine of theta simply becomes y. Cos of theta simply becomes x. Cosecant of theta becomes 1 over y. Secant of theta becomes 1 over x. That's all I'm saying at the top of this screen. And by the way, again, these 3 reciprocal trig ratios are connected to the 3 primary trig ratios by those equations, which are on your formula sheet. All right, on the coordinate grid, trigonometric ratios, whether it's sine of theta, cos of theta, or tan of theta, can be positive or negative depending on where things are. Now, look, you don't want to memorize this formula. If I just take a look, for example, at, it doesn't matter, I'll pick one, cosine of theta in quadrant 2, I know cosine of theta in quadrant 2 is negative because in quadrant 2, x is negative, and cosine is x over r. If I say to you, well, what is tangent of theta in quadrant 4? I would say to myself, well, I know tangent of theta is y over x, and in quadrant 4, x is positive and y is negative, so I would have negative over positive, which is negative. Now, this is very important when you're finding x, y, and r, because if I go back over here to this basic idea of all of these trig ratios being defined by x, y, and r, invariably you're going to have problems where you have to find a missing parameter here. Maybe you know x and y and have to find r. Maybe you know x and r and have to find y. And that means, I'll pick on finding y, that if you're using this highlighted equation to find y, you're going to have to take the square root at some point. And that means you're going to have to go plus or minus. And that means you're going to have to look at the question and decide whether you want to go with plus or minus for y. Because if in the question says that we're talking about quadrant 3 for the location of the terminal arm, then when you find y and go plus or minus, you're going to have to go with the minus because in quadrant 3, y is negative. So all this page is reminding you is to be mindful of the different quadrants that you're dealing with, because the numbers that you want to use may be positive or they may be negative. How do we solve trigonometric equations? Well, there are a couple of ways to do it. I'm going to go with the method that everybody should be able to use. So there's a second method that I think is better, but some students struggle with it. So this is a method that everybody should be familiar with. And by the way, this method is a method you do need to know how to use, because the second method that we'll get to doesn't always work. What you do is you identify the two quadrants that the terminal arm may lie in and find the reference angle on your calculator. So for example, if I had the following equation, and I'm going to go with a very simple equation, I have tangent of theta equals negative 1.6. I would say to myself that the two quadrants that that angle could be in are quadrants 2 and 4, because in quadrant 2 and 4, those are the two quadrants that tangent is negative in. I would use my calculator at this point in time. And let's just say that I wanted to do this work in radians. I wanted decimal answers in radians. So then what I would do is I would take the inverse tangent of 1.6. Remember, we teach you this at WCHS all the way back in grade 10. When you find angles on your calculator, you never put negatives in for the argument of the inverse. So we just use 1.6. And what we're getting is 1.01 radians. So what that means now is that I know, if we take a look at the next step here, sketch the reference angles in the two identified quadrants, I know that I have 1.01 rads here and 1.01 rads here. That's the second step. Then it says use your sketches to determine the rotation angles. Well, the rotation angle is going to be what I'm going to draw in blue. That's the rotation angle, and this is the rotation angle. And this goes back to my discussion earlier about the connection between reference and rotation angles. This rotation angle theta would be pi minus 1.01. This rotation angle theta would be 2 pi minus 1.01. And I'm not going to work out what those numbers are. Those would be the two solutions. So this is one way in which you could find the solution to that problem. However, and this doesn't always work, if possible, use the coordinates that you are familiar with on the unit circle. Well, that's not helpful in solving the equation tan of theta equals negative 1.6. But it would be helpful if you had cos of theta equals negative root 3 over 2. Because then you can just look at your unit circle and know the two locations in terms of rotation angles that give that cosine. By the way, you could still solve this equation at the top of the screen using your calculator and reference angles. But if you wanted answers in radians, you would put your calculator into degrees, so you would recognize the reference angle. And the reference angle, by the way, would be 30 degrees. One final comment about solving linear trigonometric equations. It might not be written as cos of theta equals root 3 over 2. It might be, or negative root 3 over 2. It might be that you have this trigonometric equation. So you simply might have to rearrange an equation to get it to that point where you can write and think of the unit circle in terms of cos of theta as negative root 3 over 2. Or to get it to the point where you can use your calculator and the concept of a reference angle. What if it is a quadratic trigonometric equation? Well, listen, when you solve a quadratic equation, you factor it typically to get two linear equations, and that's all you do here. You factor the expression that's equal to 0, and you set each factor equal to 0. As I probably said in the first video, I don't think I've mentioned it here, I have mentioned that the purpose here is not to go through a bunch of examples. Especially in this video with trig, a lot of what we're talking about, you need to go to your notes and look at the examples that would connect to this. There are tons of examples here that we have done, and tons of examples in your review handouts dealing with trigonometric equations. You need to know the properties of the graph of y equals sine of theta and of y equals cosine of theta, and you need to be familiar with the terminology. So, for example, the amplitude of either of those graphs is 1. The period of each of the graphs is 2 pi, or 360. The start point of a sine graph is at the origin, whereas the start point of the cosine graph is at the top. You need to know where the x-intercepts are. You need to know what the y-intercepts are. You need to know all of the properties of these graphs. And you also have to be able to compare them. I think it's obvious, but just in case it isn't, these two graphs are identical except for a phase shift of pi over 2. If I take y equals sine of theta and shift it pi over 2 to the left, it becomes cos of theta. If I take y equals cos of theta and shift it pi over 2 to the right, it becomes y equals sine of theta. These two templates, I guess I'll call them, are on your formula sheet, and these are used to explain and describe and work with transformations of y equals sine of theta and y equals cos of theta. In these equations, if you take the absolute value of a, we can certainly think of the absolute value of a as a stretch factor, and it is, but in terms of these functions, it's better to say the absolute value of a is the amplitude. D is what's called the vertical displacement. C is referred to as the phase shift. The period is 2 pi over b. The period is given the symbol k, and k in this context is not the same as the k when we talk about translations. That's something different. If you want to work in degrees, it's 360 over b. D is also sometimes referred to as the median value of the function or the midline. It's where the middle of the function is. The maximum value of the function will be wherever that vertical displacement or midline is, plus the amplitude. The minimum will be whatever that median value of y is, the midline or the vertical displacement, minus the amplitude. That's taking us now to the tangent function. You need to know the properties of the graph of y equals tan of x. I believe we're into Unit 4 now, although I don't have a title page here for Unit 4. This is something that we covered in Unit 4. Listen, I'm not going to spend time right now with you, but if you take your graphing calculator, put it into degree mode or radian mode, I don't care, and go y equals tan x in your y function list and go zoom trig, you'll have a picture of what I'm talking about. You need to know that the period of this graph is pi radians. It repeats every pi. You need to know where the vertical asymptotes are, where the x-intercepts are, all of that information. And although You're not supposed to be expected to worry about transformations. I think it's valuable to know how to transform that graph that you're looking at on your calculator to other forms of it with the parameters a, b, h, and k. You have to know how to solve trigonometric equations graphically. Listen, you can solve trigonometric equations algebraically, but sometimes it's not possible, and sometimes it's a lot more efficient to do it graphically. You would never solve any equation graphically, though, if you were doing a written response question. Basically, what you do to solve a trigonometric equation graphically is for y1, you enter whatever the left side is equal to. For y2, you enter whatever the right side is equal to, and you find the points of intersection. Or you could zero the equation and simply graph the whole thing as y1, and the x-intercepts will be the solution. But those strategies for solving trig equations graphically are true and useful and used in the same fashion as solving any equation graphically. If you were going to do this and you wanted to know angles in radians, but you wanted exact values like 3 pi over 4 or 7 pi over 6, then you should put your calculator into degree mode even if you want answers in radians, because otherwise you won't recognize those special angles. Applications of sine and cosine functions. This is where we're talking about tides, Ferris wheels, times of sunrise, frequency of a siren that oscillates. This is where we use these two transformations of sine of theta equals y and cos of theta equals y. Always solve applications graphically. Now, I think that the handout I gave you might say algebraically. I don't know. I'm at home right now, and I have a couple of versions on my computer, so I can't see which one I printed out for you. I think it might say algebraically on your handout, but it's graphically. You never want to solve these problems algebraically. When graphing these trigonometric application functions, graph them over one period and set the vertical window settings to go one amplitude above and one amplitude below the displacement. I know that I said we weren't going to do a lot of math, but I do want to give you an illustration of what I'm talking about here. Let's imagine that you have the depth of water in a harbor, and you're given this. The depth of water in a harbor is negative 12.8 times cosine of pi over 6 times t minus 1.2 n bracket plus 16. All right? Forget whether or not that's a realistic physical situation or not, but this is the depth of water in the harbor. In order for us to see one complete cycle on our graphing calculator so that we can do some work, you have to know a number of things. So for example, the amplitude is 12.8. The vertical displacement is 16. The period is 2 pi over b, which is 2 pi over 6. And, you know, yeah, you can multiply by a reciprocal instead of dividing by a fraction, but I like instead the thing that will always work, which is to multiply by whatever you need to get rid of fractions. And in this case, the 6's cancel, the pi's cancel, and you get a period of 12. So what I'm saying on the previous page is you want to graph it over one period. So for your window settings, you want to choose a minimum x of 0 and a maximum x of 12. You want to look at one complete cycle of this graph. On the previous page, the one that you're probably still looking at if you have the handout in front of you, I said that we want to look at one amplitude above the displacement and one below the displacement. Well, the displacement's at 16. And one amplitude above would be 16 plus 12.8, which would be 28.8. And 16 minus 12.8 would be, I think, 3.2. So you have to set up your vertical window settings to see those numbers. And I would probably just set it to a minimum y of 0 and a maximum y of 30. So with that being said, and again, I don't want to spend too much time doing specific examples, but let me show that to you on my calculator. I'm going to put in the function y is equal to negative 12.8 cosine, and then I have pi divided by 6, and then I'm multiplying pi divided by 6 by x minus 1.2. I'm closing the brackets twice, and I'm adding 16. And my advice has always been to students, before you get out of a screen where you can no longer see what you've typed, just double check to make sure it's right. And I think it's right. So if I were to go graph right now, I may not see anything that's useful. Now, I kind of lucked out here because I happen to have some window settings that are appropriate. If I would have gone zoom 6, which is standard, I get something which is maybe useful but not really appropriate. By the way, if I go zoom trig, might not see anything. I don't know. Well, there's a little bit of it. My point is, these window settings that you've got on the left-hand side allow you to cleanly see one complete cycle. We're going to go from 0 to 12 for x, and you can go to a little bit more. I'll go up by clicks of 1. And for y, I'm going to go from 0 to 30. I'm going to go up by clicks of 5. And if I go graph now I get a pretty decent graph that I can work with. So if the question was, what's the first point in time? The time would be given in hours after midnight, I suspect. What's the first point in time where the depth of the water is 15 meters? Then I could graph y equals 15. I could find out that first point of intersection and get the answer. This is why it's paramount that you set up your window settings. And had I been thinking a little bit more forwardly, I would have chosen something that we wouldn't have seen anything with normal window settings. Anyway, you've got to set up your window settings that way. You solve these questions graphically, and for goodness sake, make sure your calculator is in radian mode. You must be in radians. I'll quickly show you something here. If I were to do this and my calculator was in degrees and I wasn't aware of it, I either get nothing, or in this case I get what looks like a horizontal line. And that can be very disconcerting to a student. There's my y equals 15, by the way, which I'll just get rid of. This can be very disconcerting to a student because they're getting a horizontal line. They know it should be a sinusoidal curve. And then you get the exam sweats, right? You go into y equals and you're wondering, what did I do wrong? My x is in there. I've entered it correctly. You're just in the wrong mode. And I would give you that advice whenever you're dealing with graphs and trigonometry. If you ever get something that doesn't look right, check to see if you're in the right mode. As well, sometimes you're given questions where you have the equation of the function, like the one we just talked about, but other times what you're dealing with is something like a Ferris wheel where you have to build the equation. And we've done examples like that. If you look in the lesson dealing with this, there's at least one example in there. Oh, there we go. Now we're into Unit 4. Unit 4 is Trigonometric Identities and Equations. This is going to go pretty quick. Even though it's very challenging, we learned in this unit that there are all these identities. There are what are called the quotient identities. An identity is a statement that's always true for all values of the variable that are allowed. So for any value of theta that's allowed, sine of theta over cos of theta will always give tan of theta. Of course, not every value will be allowed because you're not allowed to divide by 0. So cosine of theta is not allowed to be 0. But anyway, tangent equals sine of theta over cosine theta, and cotangent theta equals cos theta over sine theta are called quotient identities. I think it's important that you know the names of those identities. These three are called the Pythagorean identities, and of course, the number of identities starts to grow quite a lot as we progress through this unit. You're not expected to memorize them, but I hope you're expecting yourself to be familiar with some. I think if you see sine of theta over cos of theta on an exam and you have to go on a hunt for what that is, it's going to slow you down. Similarly, sine squared theta plus cos squared theta is 1. And the reciprocal identities are those. We also learned about the sum and difference identities. And for sine, there's a sum and difference identity. For cosine, there's a sum identity and difference identity. For tangent, there's a sum and difference identity. And then we have double angle identities. This is what I mean by this is going to go quick. This is the double angle identity for sine of 2 alpha, or 2 theta if you like. This is for tan of 2 alpha, and this is for cos of 2 alpha. Cos of a double angle has 3 different forms. So what exactly are you expected to do with any of those identities? Well, you're expected to be able to work with them and simplify expressions. And my list of strategies that I gave you earlier on in the year still holds true. If you want to simplify an expression, try changing everything to sines and cosines. Remember to keep an eye out for parts of any known identity. So if you're working on something and you see sine squared theta plus cos squared theta in your work, well, you know what that is. That's 1. Factor if possible. If you have fractions being added or subtracted, bring them together by finding a common denominator and adding or subtracting them. And this is maybe the best piece of advice. Whatever you're doing, if things become too dark and too confusing, then go back and try a different path. And everything you're looking at on the screen is a list of strategies for simplifying trigonometric expressions or rewriting trigonometric expressions. If you are solving, not solving, if you are proving a trigonometric identity, and I would say it's very likely that you'll see a trigonometric proof on the written response of your exam, you follow all of the same strategies. Remember, everybody, that the idea behind a proof is you want to work on the left side and the right side separately, and you want to manipulate the left side by doing all of this to turn it into the right side, or manipulate the right side by doing all of this to turn it into the left side, or by working on each of them separately and finding a middle ground. But you still do all of this. But if things become too messy and cluttered, then go back to the beginning and try a different path. There's one more thing, though, when you're proving an identity. You get focused on working on, say, the left-hand side. Keep your eye on the other side of the identity so that you know what it is you're after. One other point here, when you're proving an identity, if you use one of the identities on your formula sheet as an algebraic replacement, you need to either write that identity down, and I would recommend writing it down with a circle around it, or just writing the name of the identity you used. So if you replace tangent of theta with sine of theta over cos of theta, you should write quotient identity beside that. Sometimes you have equations, and in order to solve the equation, it requires the use of an identity to change it. So, quick illustration of what I'm talking about here. If I have 1 minus cos 2 theta equals 0, you don't know how to solve that trigonometric equation graphically, but if you put in for cos 2 theta 1 minus 2 sine squared theta, which would be the smart move because the 1 minus 1 cancels, you would have 1 minus 1, which is 0, and then minus negative 2 sine squared. You can divide both sides by 2. I'm working right to left here. Actually divide both sides by negative 2. Take the square root. Since we're taking the square root of 0, we don't need to worry about plus or minus. Now you're down to sine of theta equals 0. And I know it's been a while for some of you since you've done this, but hopefully you remember that since sine of theta is the y-coordinate on the unit circle, you're talking about any two locations on the unit circle that are here or here. These are the locations that make that equation true. So solutions would be 0, pi, 2 pi, negative pi, and in general, multiples of pi. Non-permissible values. Remember that to find non-permissible values for an identity or for an equation involves looking at any value of theta or x that makes division by 0 happen. Now I want to discuss something with you here, because if I had, and this is the last thing, but I want to make sure I go over this with you because on your exam many of you made this kind of mistake. If I had some expression that had, doesn't matter, cosine of theta over tan of theta plus 4 over 1 minus sine of theta, then what you would do is you would say that tan of theta is really sine of theta over cos of theta. Then we have 1 minus sine of theta. And what I've taught you to do in class, and some of you on your exam actually just had highlighters and it worked out beautifully. What I've taught you to do is say that, well, this is a denominator, this is a denominator, but this is also a denominator. So what we end up writing, we actually have 3 denominators here, is we write that sine of theta over cos of theta is not allowed to be 0, because that's a denominator. We write cos of theta is not allowed to be 0. We write 1 minus sine of theta is not allowed to be 0. This first statement, I can multiply both sides by cos theta and get sine of theta is not allowed to be 0. And I forgot to put not allowed to in all of these, so let me do that. And what some of you on the exam did is you stopped here, here, and here. You may have even said sine of theta here is not allowed to be 1. Well, those are all true statements, but when I say what are the non-permissible values, and when the diploma exam says what are the non-permissible values, we want to know what theta is not equal to. So you're not done. You need to say that sine of theta is 0 at 0 and pi, so you would say 0 and pi are non-permissible. Cos of theta is 0 at pi over 2 and 3 pi over 2. Etc. I'm not going to finish the problem. I just wanted to make that point that you're not done when you say sine of theta is not equal to 0. You have to tell me what theta is not equal to. That is all of Unit 3 and 4 in Math 30-1, the straight poop.